Welcome, my friends, one and all. I see we've got the Green Observer in the chats and Mr. Will Stevenson. Thank you guys for joining today. Today, we are going to be discussing how we can possibly cut off the ends of our beams and they won't fail. We're not going to cut off the whole end of the beam, obviously, because then it won't be on the wall. But hey, that's what we're going to learn today. So hopefully this is good learning content. But the first thing is that you should know that not only do I talk about cutting off the ends of beams on YouTube, but I also teach and have a course on home building as a whole and a framing design program on my school server, which you can check out in the description, www.skool.com/bfbsuccess. If you want to, one, learn cool stuff about houses, two, join a community that's got some cool guys in it that like to build stuff. We share projects, yada, yada, yada. And three, get a daily dose of some information or stories from myself as I post them. So let's just hop right into it here. So the audio a little crunchy, just me. Ooh, that would be good to know if it is crunchy. Hey, other colors of observers, would you verify or not verify that? Put a 1 in the chat. Put a 1 in the chat if I got a crunchy audio. Make sure it's plugged in all the way. Mute, unmute, plugged in all the way. Well, while we're waiting on a response from that, there is a better colored observer in the house. Wow, okay, my audio is crunchy. That's not good. Let me see if I can fix by disconnecting and reconnecting. Make sure I disconnect the correct. All right, now I'm unmuted. Did the audio get any better? Put a 1 in the chat if the audio is still bad. Actually, put a 2 in the chat. That way I can differentiate. Put a 2 if the audio is still bad. Put something else if the audio is better. And hopefully wait. Oh, much better. Cool. The old on-off fixes things. Excellent. Well, if you didn't hear me before, you should join my school server. Link in the description. Thank you, Green Observer. Cool beans. So let's just get right into it here. 69.420. 5555. I like it, observers. I like that 5555 Quattro Cinco. All right. So what is cutting off the end of a beam? And why would we do it? Well, let's just kind of figure out why would we be cutting off the ends of a beam? It'd be best to leave them whole, uncircumcised and all. You got a beam end and it's sitting on a wall. This is a side cut view, right? So that's a beam. It's sitting on a wall, right? You would ideally just leave the whole beam there. And sometimes you don't even have to cut the end off, right? You can let it hang out over here. No one's upset by that, right? So that's cool. That's a way we can do things. But sometimes we can't do that. And why not? Well, we can't do that sometimes because sometimes our beams have to sit on walls that are covered by other things. So, for example, you're typically going to see this in like a garage or a large open space that has a roof landing on one of the walls of that space. And I'll show you why. A cross-section of the wall at the top of the wall of the exterior wall where that roof is landing would look something like this. The wall comes up. You got two top plates. And then you're going to have some kind of, let's say this does this, right? You got some kind of rafter doing that. That's sitting on your wall with a bird's mouth cut on it. Okay. Now, if your room is over here and your beam is going in a different color and your beam is, just landing on the wall and it's going this way into the room and the end of the beam is right here. Well, we can't let the beam be square. If that's the size of the beam, we can't have this sticking out above the roof. So what we have to do is we have to cut that off. And so what I'm going to do today is prove to you why in most cases that's fine, right? So you have to at least cut it off to plane out with the rest of the rafters so your roof sheathing can go on top of that. Now, in extreme cases, you're going to get like, it's going to get real skinny back here, maybe like 2 to 3 inches, and it's going to taper up real low. And what makes this a problem is, one, if these are regular 2x6 rafters, that gets pretty small. And two, if this roof pitch is low, it's going to push the notch out really far. If the pitch is super steep and the rafters are, like going way up like this, then there's hardly any notch on the beam. So it's cool there. But some cases we got to do this. So that is why that would happen. That is why that would happen. And so frequently we have to make notches and things. But make the beam yellow. I like red beams. Okay, I don't have yellow as a color, unfortunately. You can work with red. So red observer is happy with the red beam. So that is why. Now, before I really explain why it's okay to cut that off, we need a little bit of background information in one of your favorite topics, which is stress analysis. Okay, so if we were to have a typical beam spanning between two things, we have a way of analyzing the stress in that beam. And the stress, for those who don't know, is how much is the beam hurting, right? We're going to put forces on the beam, and the forces are going to make the beam feel stressed, right? So if we take a load and we put it in the center of the beam, then what's going to happen is we need to think about, what is this beam feeling? We need to know what this beam is feeling in order to know how to solve this problem. So what we do is we simplify the scenario and we say, oh, okay, well, this beam is just a fixed object floating in space, and it's got something pushing on it down there, and it's got something pushing on it over here, and something pushing on it over here. That didn't come out well. Okay, so now it's just a fixed object, a rigid object. So what we're going to do is we want to basically analyze what's happening inside this beam, so we understand where are the stresses in the beam. So we know if we cut stuff off, you could ask the beam how it's feeling, says Will. That is true. We could ask the beam how it's feeling. Unfortunately, they cannot talk because they are glued. Their mouths have been glued shut in the manufacturing process, unfortunately, so they can't speak. But that's what we would do. So we would try to figure out what's going on. And the way we do that is, for something simple like this, is we would draw what's called a shear and moment diagram. For those of you who have taken engineering in any capacity, or physics maybe, you have seen shear moment diagrams. Okay, so a shear diagram is basically saying, along the length of the beam, what is the shear stress that the beam is feeling, right? And what is the moment, or what is the moment that is acting on the beam? Sorry, that's not correct. What is the shear force acting on the beam, and what is the moment acting on the beam at any distance along the length of the beam? We're not talking about stress yet. We're not there yet. Okay, so this is shear, which I believe we normally just do tau or something. And this is, nope, shear is, that's stress. I'm not talking about stress. I'm confusing myself. Shear is V and moment is M. V for shear, because shear starts with the letter V. So what you're going to look at is basically, the whole point of this is we want to be able to chop the beam at any point and say, what does, if this is the beam where we chopped it, there's going to be some kind of normal force. There's going to be some kind of moment, and there's going to be some kind of shear, right? So what we're concerned with in this like beam scenario, we're not concerned with the normal force, because there's nothing like pulling the beam over, or there's nothing squishing the beam in. It's just moment and shear. Okay, so that's why we're not concerned with this dude. But that is what we're doing. It's like, that's a cross section. That's the slice point. So we're trying to analyze that, because we need to know right up next to the end what's happening inside the beam, so that we can know what happens when we cut it, right? So the way this works is, let's say there's some load here, and we analyze this. If we were to cut this off, let's say right here, you basically do this thing, and you solve for, let's see. So this is where it's supported. That's the thing. Okay, so right on this end of it, there's some force pushing up on this. And all the forces has X, Y, Z's, they all have to equal out to 0, because the thing is not moving. The beam is not moving. And so there's going to be some kind of resultant shear force that's the same as that support. Where, like at any point along this. Okay, so that's pushing up. So that means this is going to push up. And that's going to be the case until you hit this new data, right? So if we were to draw this again over here, so if we're coming out like this until we, like, if we go past this point now, our little thing looks like it's got a force up over there. It's got a force down here. And now the number changed because now this object, in order to equal out to 0, has a number there and a number there. So that's going to be a different number. So what that's going to look like, I'm going to summarize this because I'm not teaching you how to do this, like, for real, is you're going to have a shear graph that looks like this. Positive, negative can flip, doesn't really matter. Okay? So that's your shear graph. And what that means is as soon as you enter or analyze the infinite end of the beam and like basically step off the wall, because there is a thickness of wall there, we're going to remember that. Okay? As soon as you come off that wall, then there is now shear force that is being exerted onto the beam, and that's going to do stuff to it. All right? And now there is a moment acting on the beam as well. So the moment is going to look basically like this. The moment is talking about, for those that don't know what a moment means, it's like bending. It's a torque. It is a force times a distance. That is what a moment means. So the moment chart is going to look something like this. It's going to go up and up and up, and then it's going to peak right there, and it's going to go down, 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 down. Okay? Now, the reason things, when you span them between two different places and you push down in the middle, presuming it's a fairly typical material, nothing fancy, it's probably going to break. If it's going to break, it's going to break right in the middle, because the middle is the maximum moment, aka maximum stress, tension being applied to the bottom here, on the whole beam. And typically, the shear is not the thing that's making the beams fail. It's this moment here. That's the bending part. So, knowing that the moment is the maximum in the center, if we're going to be cutting off the ends of the beam, we don't really care what the moment is doing. So, frankly, we can just erase it and forget about it. Okay? We don't care about the moment when we're analyzing beams cutting off the ends. We care about the moment when we're analyzing stuff, and I'll show you some numbers later. So, this is the shear diagram. Okay? Now, we figured out that shear is the problem on the ends. And now we're going to talk about a little rule that I happen to know, and I'm not going to look it up in the book, but I read it out of a book, and it's one of these special, bunch of people in America agree that this is how we do wood stuff books. And it says that on the end of a beam, if your beam is supported on a thing, doesn't matter what the thing is, you may notch the end of that beam in certain ways. And basically it tells you equations and stuff. So you can effectively notch it one of two ways. Either you have a smooth gradual notch, which changes dimension across the end of the beam smoothly, which would look like this. And it's smooth because the height of the beam is consistently changing along a linear line for the notch, right? That's one way of it being notched. The other way of this being notched, let's change colors again. Wow, that's a very interesting thing to say, Tam Tam. I'm going to bring that up. Just one question. When do you sleep? Interesting. Alrighty, back to work here. So the other way to notch this is with a square notch, which would look like this, right? You take a big old chunk out of the corner. Now, both of these notches would allow this beam to fit under some theoretical roof line, right? But one of them does something way worse to the beam than the other one, and it does what's called a stress concentration. Anytime you have a sharp corner in a material that's being stressed, oh, my headset likes to turn off randomly. That's always nice. Let's turn it back on. So anytime this happens in a material that's being stressed, there's going to be basically a bunch of owie pain that's concentrated right here that makes this thing want to break right there, and just bad stuff happens. So we want to avoid stress concentrations. Now, the blue notch is worse than the red notch because of the stress concentrations, and that's manifested by the equation that governs what you're allowed to do with this notch size. So there is an equation that says if this distance is this, and this distance over here is this, and this thing is this long and this deep and this, then this is the notch you're allowed to make, right? And it's worse than, it allows you to get away with less than the smooth red line, right? The smooth red line is basically like, let me say the rule. The rule of the smooth red line is if you, let me say this carefully so I don't say it wrong. Okay, so you've got a beam sitting on a wall and you have a smooth red line notch. The rule is if you make this change gradual, linear, and consistent, then the end of the beam will only fail if you basically pretend and the beam doesn't fail in shear if the beam is the nominal size of the end of this. So basically you're imagining a beam that's actually that size all the way across whatever you're doing. So if that beam doesn't fail in shear only at that size, then this is allowed. Then this passes. And that makes sense because, obviously that wouldn't work with moment. If you made the beam that small, then the moment would fail and then it would break in the middle and you'd be unhappy. But we don't care about the moment. The rule says if this thing passes in shear, when I'll show you a little chart here to make it a little more obvious, then you can do this, right? And we'll talk a little bit about how this height can move around left, right a little bit when we really need to squeak the numbers in. But that's the basic concept. So let's go ahead. Let's see. Do I need to talk about anything else? Normal shear. Okay, so notch types that affect shear. So yeah, that's the basic thing, right? We want to be able to make that gradual notch, which works on a roof that's sloped and gradual as long as we follow it. But we need to know that basically when we stick this beam on this wall with this size rafter and that pitch, that we have enough material left over right here that it's going to do its job and the shear is not going to be a problem, right? So that's what we are going to check. So let me hop over to my computer and I will share my screen and show you guys in some calculations why this works. So this is my first time doing this live. So we're going to share this tab. Okay. And it looks like it's streaming and my head's still here. So you can still see me. That's great. All right. So this is a software that I use to do some beam calculations and stuff. It's pretty cool. It's free. Anybody can do it. This is what I show you how to use in my framing design program that you should all watch because you want to learn as much as I know. But this is how we do this. So what's going to happen is I have this beam in here and the spans are defined here where it says spans and supports. And I said 24-foot span end to end for this beam. Okay. This problem, we're typically only going to have this problem with big beams because big beams are tall and tall beams would stick out above the roof. So this happens in garages or large open areas. So garages are typically 20 to 24 feet deep. And that's where we have this issue. So that's why I made it 24. And loads, I said, go ahead and throw on a 12-foot tributary width of dead load 15 pounds per square inch, pitch of 512 for the roof, and then floor 10 pounds per square foot, live load, roof 20 pounds per square foot, live load. Okay, those are just standard numbers that I'm pulling out. I'm just creating a uniform load on this beam. That's all that means. You don't really have to matter. Doesn't really matter. Okay, so product selection. This is where I'd go through and I'd pick one out. I'd pick out a beam product. I'd pick out something and say, I think this will work, and then I'll go try it. So I go to solutions. And solutions tells me if I pass or fail. Now, this beam passes. This is a 5.5 inch by 16 inch 24F V4 DF glue lamp. So that basically means stuff. You don't need to worry about the classification, but DF means, Doug fir. But that's the beam that I've selected. Now, if you look at the ways this thing passes or fails, there's different categories here. Remember, I was talking about moment. Well, this says positive moment is this many. I believe it's in foot pounds or inch pounds, one of those two, at this distance. And that distance is 12 feet, 3.5, which happens to be in the center of 24 feet. So look, it's telling you the moment makes it fail in the middle of the beam. I'm allowed to have 55, yada, yada, yada. And I'm passed because I'm 64% capacity. So if I use this beam and that loading scenario, then I don't break because I'm at 64% capacity. Now, what are these other things telling you? Well, these are live load deflection and total load deflection. These basically tell you how much is the beam bending. So this is saying under maximum loading scenario, total load, everything all at once, you're going to have 1.1 inches of bending down in the center of the beam. Worst case scenario. Now that will probably never happen, but that just tells you these numbers. So Now, what else does it tell you? It tells you the member reaction, which is saying how much weight is like acting on the end of this beam, and it's basically telling me there's about 6,000 pounds on the end of this beam pushing down on the wall. That's kind of neat to know. And what it's telling me with the past 73% is telling me that I'm not crushing the wood at the end of the wall with that much weight based on the size of my beam and the area of the wall and yada, yada, yada. So now the last thing is shear, right? Remember how I was talking about how shear is rarely the thing that makes us fail, but when we're considering the end of the beam, we have to think about it. So this is 27%. So we don't fail here, okay? We're not even close. Moment's the thing that's going to make us fail. So what happens if I take the load and I make the load more? I'm going to make it way more, like 18 feet of tributary width. And I go back to solutions. And all of a sudden I broke. Actually, I didn't break. I crushed the wall and I almost broke. Okay. So the breaking part is the moment. And I'm 95% capacity. So that's really close to breaking. You know, if you have a defect in the beam or something, that might break. And then the member reaction is saying, hey, I've crushed the wall on the end. I have too much weight on the end now. And then shear, oh, look, shear's still at 39%. Okay. So you can see how shear is much less affected. So what we're going to do now is we're going to go back to loads. We're going to put this back to 12. And remember, we're concerned with, does shear fail at the cross section of the smallest part of that notch we made? So let's say we had a 16-inch tall glue lamb and we had, I don't know, let's try like 5 inches or something. So we go back to product selection and we want to know, what is the smallest glue lamb we can pick? Well, it's a 6-inch tall glue lamb. So does a 5.5-inch wide, 6-inch tall glue lamb spanning 24 feet, this would be a ridiculous size. It would be way too bendy, right? You're going to see what's going to happen here. Look at the solution. This broke in the middle by 421% capacity, right? So this wouldn't work at all. And the total, like the center of the beam dropped 20 inches, right? So this is way too bendy. But remember the rule. The rule is if shear doesn't fail at that dimension, then you're fine. And look at shear. We passed by 75%, right? And we're still good. So what this tells us is that I'm going to get out of this thing now and go back to just me. So what this tells us is that if we have a beam sitting on the wall and we cut off the end of the beam, but this dimension back here was 6 inches, then we don't care. We could lose all this material and we have a smooth line here. All of the weight and stress from this beam is going to transfer down through that smoothly to the wall, and there will not be any problems according to the rules of the wood design people. Cool. So that's how that works. Therefore, so let's take a look at the chat here. What we got going on? Will Stevenson says architecture is his forte. That is correct. I do like the drawing. That is a cool thing. And Blue Dot says I can't see anything. Bright Green says I can, don't listen to him. Green Observer 100%. Wait, I can see everything. Oh, I see what's going on. Blue Dot said I can't, and Green Observer says that I can. That's because the Green Observer is the real observer. Observe harder. Look at that. I love it. And I'm watching YouTube via Braille. Well, thank you, Blue, for actually popping on and feeling out how this show is going. I appreciate it. And Tam Tam says, I love the depth of explanation here. I appreciate that, Tam Tam. I aim to please and I aim to teach the nerdy stuff that like nobody really wants to hear. And that's why you're all here. So that is that's the basic premise, right? So we can take beams. Oh, I'm going to go through one more little nuance here. And we can cut off the end of that thing. Now, here's the real trick. If you have a wall and a beam and the beam is notched, what happens if all I have left here is like 2 inches? Well, I don't really have a way in Forte to design a 2-inch beam. Profanity going on in the chat. The Bright Green Observer says the real Green Observer. Yes, there is one real Green Observer, and he is the dark one, the OG. Or should I say the GO because it's green observer? Y'all are golden. I love you guys. So if this is 2 inches, we can't really go into Forte and say 2-inch beam because they just don't have an option for specifying that. So what do we do? Well, here is the trick. I don't really care what this dimension is on the end of the beam. Why? I don't care because I didn't need it to be there. I could have cut that off too, right? So now you're asking yourself, well, if we can cut off all of this and we can cut off this, well, like what's the point? What am I doing here? How much do I need right here? And the answer lies within the stars. The answer lies within the stars. The answer is in the table. The answer is in the book. Okay. So in this book, I've got NDS supplement and design values for wood construction. These tables tell me stuff about pine. Okay. So Southern Yellow Pine, number 2 grade. I'm concerned about the top plate right here. I don't want to crush the top plate. I want to know how much of this I can remove in order to get this number boosted up to 5 or 6 inches so that I know the beam is fine, right? So I would look at 2 to 4 inch wide, number 2, compression, perpendicular to grain, remember, because that's what we learned about last time. Compression perpendicular to grain is 565 pounds per square inch. 565, folks. So 565 PSI is what a top plate of Southern Yellow Pine could typically bear from this beam. So there's some massive force happening right there, right? And it has some area on the wall. Here's the area. Now, what is this dimension? That dimension is the width of the beam. This dimension is the depth of the wall. Or in this case, if we don't want to do the full depth of the wall, what is this depth that we have to leave behind so that the beam won't crush the wall? Let's find out, okay? So we knew that this beam under this typical loading scenario had, I'm not going to show you the number again, but the load was some 6,000, I think. Yeah, it was about 6,000 pounds. Okay. There's about 6,000 pounds on the end of this beam pushing down on the wall. Okay. Well, 6,000 pounds, calculator, because that's what we engineers do, divided by 565 pounds per square inch gets me 10.6 square inches. I need 10.6 square inches of area right here in order for this to work. So what is the width of the beam? Well, we know the beam was a 5.5 inch wide glue lam. So if I divide that by 5.5, then I need 1.9 inches, right? Isn't that crazy? Isn't that absolutely bonkers? Let me erase this and get a little more clear here. Okay. So 1.9 inches, let's say 2 inches. So if I've got this beam sitting here and I've cut off all the top of this and it's sitting on the wall, and this is a regular 2x4 wall. That ain't even a 2x6 wall. Now, it might need to be a 2x6 wall for the column support for 6,000 pounds, but that's a different topic. We're not going to talk about that. So let's say it's a regular 2x4 wall. Then that means this is 3.5 inches of framing it's sitting on. We could cut off 1.5 inches off the end of this beam, and it doesn't even need to be there, right? So this is how we know. It's because this little magical area in here where that beam is sitting, that's where the magic happens, right? So that's why you make sure if your beams have like defects or weird stuff happening right here, like this is an important place. And you wouldn't want to really try, like you want to get as much area as you can. But that is an extra trick if you're having a hard time getting that end number, what you need it to be, you can actually remove more off the end of the beam. Like you wouldn't, for the math purposes, you could remove more off the end of the beam. If you were actually framing this, you wouldn't cut off the end of the beam if you don't need to. Like you just know that it's extra wood. And okay, so let me catch up on the chat here. Tam says, I totally want to learn about this kind of stuff. Good, Tam. Then you should join Bungalows for Bachelors on the school server, and you can watch all of my classes. And, of course, continue to watch the live streams because that is where I have the freedom to be fluid with my conversation. And I get to interact with you guys, which is great. Oh, let's see. Will says, because you care about the inside height, he's guessing. I'm not sure what inside height you're referring to. Let me talk about one more thing that's never going to be a problem either, right? So, where Will said inside height here, I want to clarify. There's another way beams fail, and this is never the case. But even if you had like a regular beam supported on something, there is another type of shear that would apply that's basically like scissors, right? What are the odds that the beam cracks along this line and the weight's over here pushing this down? So it would basically look like this moves up and that moves down. It would shears off right there. That like could matter, but that's never the way beams are going to fail. They're going to fail when I say shear, they're going to fail in horizontal shear. What that's going to look like is a delamination of the beam. So a glue lam beam, if you've ever seen it, basically like a 5.5-inch wide glue lam beam is just a bunch of 2x6s, approximately, that have been glued one on top of the other, and their seams have been stacked and staggered so that it's all one big chunk, right? So what would happen is if you had a beam with a bunch of, plies in it, look something like this, then you had a horizontal shear failure. What's going to happen is these are actually going to become disconnected at these glued plies. And most likely they're actually not going to do that. They're probably going to like fail inside the wood because frequently the glue they're using has a higher shear strength than the wood itself. So it's actually the wood that's going to fail. But yeah, that's how that would happen. If you want to understand shear strength in that context, we might be able to look at something like anything with paper, like lots of paper, right? So if I take this book and I turn it like this, the spine has some rigidity to it. And if I hold it up on the ends, it's going to have some kind of shape. It's going to hold that shape. But if I turn it this way and I try to hold it up on the ends, see that? That is shear slippage between each sheet of paper. They are slipping past each other, which is why it gets, this shape on the end, right? That's a type of shear failure. They're slipping past each other. So imagine this happening to a big wood beam. That's what it looked like, right? So hopefully that clarified some stuff. Tam asked, steel or wood beam is better? Well, that depends on your budget and your scenario. Every now and then, a residential structure is going to require a steel beam because wood beams either are just prohibitively large and expensive and complicated, or there's like an architectural restraint keeping you down to size, right? Sometimes beams made of wood are just too dimensionally large and they won't fit into a space. And so they will use a smaller steel beam because it's going to be a little stronger, like per dimension. But as soon as you introduce steel, you're introducing a whole bunch of other complex restraints, and you need steel posts and you need all, like, which just goes way more complicated to do that with steel, putting steel in it. One yellow observer says stealing is generally frowned upon. That is true. Tam out here committing crimes. That's very possible. And Will says set limit orders to 12% slippage. That sounds like something that a crypto person might know about. Tam, I can't even spell construction words correctly. I don't even know what you misspelled. Oh, steel. Wow. Yep. That's okay. That's okay. We're here to learn about construction, not learn about spelling. All righty. So that's what's going on here. That's how we can solve the world's problems all at once by notching the ends of beams. So that's all I got for you guys. Remember, if you want to learn more about this kinds of stuff, I go through and I've got it in my framing design program and my home design program, my home building program in the school server in the description below. Otherwise, just keep hopping on for these free live streams, and we'll just keep learning about interesting things. And thank you, Tam, for liking this. I do not know what's next at this time, but as soon as I hop off the call and go to sleep and then wake up in the morning, I might know. But I think about one thing at a time. If you have any questions, if you guys have any topics that you like, well, hey, when you frame a house, like how does this work or how does that work? You are welcome to ask, and we might just talk about it for topics, because I'm always looking for interesting topics. So a lot of the stuff I'm going to talk about is going to be the stuff that I've come across in my time as a structural engineer designing custom homes, being like literally having to think through these problems. The only reason I know this is because some guy somewhere had some massive beam and we had to cut most of it off at the end. And I was like, can we do that? Is that okay? And I just had to go read the books. And I was like, oh, there we go. Cool. So I'm just sharing that with you guys. And hopefully now you guys know that you can cut beams off and stuff. So you don't have to freak out, or you do freak out. Thank you, Will, for posting the school link in the chat. I appreciate that. Yeah, if you guys, also I do have another business where I actually draw. I am a draftsman. So if you want house plans drawn and it's under 5,000 square foot of a house, and if you keep it between you and me and over 5,000 square foot, we can do that too. But I didn't say that. And yeah, I can draw everything up to a fourplex multifamily unit legally. And yeah, check it out. That's called Stevenson Integrated Designs. And if you just hit me up on Bungalows for Bachelors somewhere, that's how I source all those leads. So do that. I appreciate you guys in the chat joining me today and learning and being part of this community. You have made this live stream so much more fantastic. So thank you, Tam Tam. Thank you, all of the colors of the observers, especially the green one, the actual green one. And thank you, Will Stevenson, as well. Hope I did not miss anybody. That said, gentlemen, it is time for us to have the outro.